Good morning, student. In this part of the video, we are going to discuss about the impedance of a string. First, let we understand what we mean by the impedance of a string. The impedance of a string is defined as the resistance to the wave motion as it propagates through the string. Okay, and there are two sources in the string which will offer resistance to the wave motion. That means as the wave propagates, the string will resist the wave propagation. And these two, there are basically two factors. Number one factor is the elasticity of the string. Elasticity of the string. Okay, by elasticity what we mean is that if a body is displaced from its equilibrium position, then it will try to come back into the equilibrium position. Okay, so elasticity of the string will try to restore the string into its equilibrium position. For example, this is a L-length string, and if we suppose if we try to disturb the string by applying a oscillating force, then there will be the displacement of the string there will be the displacement of different element of the string, and therefore the string will try to come back to its original position. It is the equilibrium position. Okay, so because of that elasticity, there will be a resistance to the wave motion. Okay, and second part of the resistance to the wave motion is due to inertia. As you know, the inertia is the property due to which a body in equilibrium will tend to be in the state of equilibrium, and a body in uniform motion will tend to be in the state of uniform motion. Okay, so as the string was initially in the equilibrium position before it disturbed by a oscillating force or before the propagation of the wave, therefore due to inertia also try to bring the string back to its equilibrium position. Okay, so these two are the major factor which is responsible for impedance of a string. Okay, there will be other factor also. For example, there may be some dissipative force present in the string, or there may be some loose mechanism present on the string system. Basically what we are going to do, we are going to ignore these two kind of external loose mechanism and concentrate on how elasticity and inertia will oppose the movement of the oppose the wave propagation. Okay, now how can we define the impedance of a string mathematically? For example, when you consider the flow of current, then the Ohm's law will give is basically V is equal to IR. Therefore the resistance is equal to voltage divided by current. Okay, we can always imagine the voltage as the source and I is the outcome. Okay, so source divided by outcome will basically give us the resistance, or in complex cases it will give us the impedance. Okay, similarly we can apply the same logic here. As you see, the source of the wave propagation should be always a oscillating force. For example, this string is here. If I started oscillate the one end of the string, then there will be the transverse wave propagate. This is the string, and I oscillate it with a force, maybe with my hand or with some other mechanical device. If I try to oscillate one end of the string, then there will be some transverse vibration produced in the string. Okay, so in this case the force will be my source here. So impedance of the string, impedance is defined as the force F, and the outcome is the propagation of wave, that is the wave velocity. Okay, so in this case we can define the impedance of the string as F divided by V. Okay, so since we are considering the transverse wave, so F we can write it as transverse force over transverse velocity. Okay, if we divide transverse wave to transverse velocity, we are going to get the impedance of the string. Let it denote by the quantity Z. Okay, so for a vibrating string, we can define the impedance always by transverse wave divided by transverse velocity. Okay, so in the next pages I am going to find out a value of the impedance of the string, and we are going to neglect any kind of dissipative force present on the string or any loose mechanism whatever may present in the string. So this media is basically looseless media, and we are only considering these two facts, elasticity and inertia, and we'll see how elasticity and inertia is going to affect the movement of wave propagation in the string. If there is no elasticity and inertia, probably once you disturb the string it will oscillate forever, but we know in real life it doesn't happen. Okay, so the string definitely provide impedance to the wave motion, and we are going to determine the value of the impedance of the string. Okay, okay, so let's consider a transverse force. Suppose due to the application of the transverse force, the string began oscillating. Okay, so this is the movement when the string oscillate. Okay, and we will say a transverse force F naught is equal to F is equal to F naught e to the power I omega t. Okay, whenever I write F is equal to F naught e to the power omega t, it means a oscillating force. Okay, and the simplest example of the oscillating force, suppose if you take one end of the string with your hand and start to oscillate like this. Okay, so the force applied by your hand will be this force only, F is equal to F naught e to the power I omega t. So this is the best practical example of a oscillating force. Just move the string like this, so this is an oscillating force. Okay, and we know there will be a tension produced at each element of the string, and let's say at this point, say this point is x is equal to 0. At this point the tension is acting along this direction, and and in other end of the string the tension will be acting at this direction. Okay, so if this angle is theta, then this angle is also theta. Okay, so this is the tension which is acting at the point x is equal to 0 of the string. Okay, so we can resolve the tension into two components. One is with the horizontal component, that is t cos theta, and the other end will be the vertical component, that is t sin theta. Okay, now the horizontal force, the transverse force we are applying here is equal to F is equal to F naught e to the power I omega t. Okay, and if the point x is equal to 0, this is x is equal to 0 point. If the x is equal to 0 is at equilibrium, that means this force t sin theta must be balanced by this force F naught e to the power I omega t. Okay, so we can write at equilibrium of x is equal to 0 point, what we can write, F is equal to F naught e to the power I omega t is equal to minus t sin theta. Okay, minus t sin theta, because this force will be balanced by this force. Okay, so if the angle theta is very small, for theta is almost equal to 0 or very less than very small force, then t sin theta almost equal to, we can write as minus t tan theta. Okay, for small angle, sin theta and tan theta value is almost equal, and we know that tan theta is nothing but the slope of a y versus x plot. For example, if this is y and this is x, then the value of tan theta at any point here will be determined by del y by del x. Here I am writing the symbol delta because y is a function of both x and t, as I have told you many times. So in this case we have to write y as equal to dy by dx. Okay, so we can write f naught e to the power I omega t is equal to minus t del y by del x at x is equal to 0. Okay, so this is known as the transverse force. Okay, so basically this equation is valid when theta is very small. Theta is very small. Okay, now what we are going to do, we are going to find out the value of dy by dx at x is equal to 0, and then we'll put the value here, and then we can find out the impedance of the string. Okay, so let me write the displacement. We know that the displacement for a string system, or for any other the transverse wave or oscillating the longitudinal wave, we can always write displacement is equal to a say sine kx minus omega t, or in complex notation what we can write a e to the power I omega t minus kx. That thing we can write. Okay, the real part will be cos omega a sine a cos omega kx minus omega t, and the the imaginary part in that case will be a cos kx minus a sine omega x minus t. Okay, so let's say it's a cos kx minus omega t, then the real part of y will be a cos kx minus omega t, real part of this expression. Okay, since the left hand part is a complex notation, basically we are going to use the complex notation on the right hand part also, so that we can compare each of the side easily. Okay, so del y by del x will give us the value a e to the power I omega t minus kx into minus I k, right? Okay, so this value is a I k e to the power I omega t minus kx. Okay, but we are interested at the point x is equal to 0, because we are basically considering the state of affairs at the point x is equal to 0. Okay, not other point. We are considering everything, all the equilibrium picture at x is equal to 0. Okay, so at x is equal to 0, dy by dx at x is equal to 0 will give us minus a I k e to the power I omega t. So this is the value we will get at x is equal to 0. Okay, now we are going to put this value in the expression. So this is expression 1. Then we are going to basically put the value dy by dx at this point. Okay, so when we put this value, we will get f naught e to the power I omega t is equal to what will be the value, minus t, and dy by dx at minus t into aik e to the power I omega t, minus aik e to the power I omega t. Okay, so tt a t I will be there, e to the power I omega t. Okay, so f naught e to the power I omega t is equal to I a t e to the power I omega t. So this term will get cancelled, and from here what we can find out, we can determine the value of a. A will be equal to f naught divided by it, f naught divided by it. So this is the value of the amplitude of the wave, Okay, now since we have written the displacement y as a to the power e I omega t minus kx in complex notation, so we can replace a with f naught divided by it. So basically this is f naught divided by I into tension of the string into e to the power I omega t minus kx. Okay, so this is the displacement of the string. Y is equal to f naught it e to the power I omega t minus kx. Okay, okay, sorry, there is a factor k here. Okay, itk, so this will be f naught divided by atk, this k. So we can replace k with k is equal to omega by c, we know it. Therefore we can write f naught divided by I into t omega into c divided by omega. This value will get e to the power I omega t minus kx. So basically this value will give f naught divided by I omega, then c over t, okay, e to the power I omega t minus kx. So this is the displacement y when we express it in the with respect to the amplitude of the applied force. Y is equal to f naught I omega c by t e to the power I omega t minus kx. Okay, so because you see why I am doing it, I am interested in finding the quantity transverse force divided by transverse displacement. Okay, so now what I have done with this substitution, I have expressed displacement, this is velocity, sorry, transverse force divided by velocity. Okay, so with this expression, what I have converted, I have expressed the displacement with respect to the transverse force. Therefore it will be very easy for me to determine the ratio transverse force divided by transverse velocity. Y is nothing but the transverse displacement. Therefore transverse velocity dy by dt will be equal to f naught divided by I omega c by t, okay, e to the power I omega t minus kx dy by dt. So basically it will give I into omega. Okay, so let's cancel I omega will get f naught c by t e to the power I omega t minus kx. So this is our transverse velocity v. Okay, so as you remember, we have defined the impedance z is equal to transverse force, which is basically f naught e to the power I omega t f naught e to the power I omega t, and now what we get, we have got the value of e to the power transverse velocity, which is basically f naught c by t e to the power I omega t minus kx. Okay, our transverse force is f naught e to the power I omega t, and transverse velocity f naught c by t e to the power I omega t minus kx. Right, now at the point x is equal to 0, this quantity will give us k dot k into x will give us 0, because we are concentrated on at point x is equal to 0, right? So we have to put x is equal to 0 here. Therefore this part will be not there in the expression. So f naught e to the power I omega t divided by f naught c by t e to the power I omega t. So this part cancel, f naught cancel, it will be t divided by